I'll go ahead and get started. So thank you, Simon, Zeming. Thank you for joining us today. And the participants out there too. Thanks for joining in our what we call our studio audience. So I'm David Fleck, the founder and one of the managing partners of Freeflow Ventures, and we started the firm going on 5 years ago now because we saw a unique opportunity to help scientific founders bring their scientific research and translate it into startup companies in both human and planetary health applications. You know, two of what I think of as like the existential problems facing humanity. But we also obviously think it's a great way to provide investor returns too, but while also solving difficult problems. And today I'm very happy to have Simon and Zeming on because they're dealing with actually a technology, a very unique battery technology, a fluoride-ion battery technology that I think has the potential to really unlock some very unique, uh, almost as an enabler, as a way to, and I'll let them describe it more, but as an enabler for some of the planetary health, solutions that are out there, just due to the unique chemistry of the of what they've discovered. So with that, I will pass it over to them. And just a reminder to everybody that, feel free to ask questions in the chat feature. And we will get to those questions as we start the more Q&A discussion, later on. But we'll start out with some, kind of an overview by both Simon and Zemang in terms of the company, what they're doing, the progress to date, and where they're taking it. So with that, pass it over to you guys, and I'll disappear for a little while. Thank you.
Thanks, David. I'll share my screen. Just give me a thumbs up if it looks locked and ready to go.
Looks
All
good.
right.
Yep.
Well, thanks everybody. Thanks for making the time to join the webinar today. We are a battery company fundamentally that deal with fluoride materials. I'll talk a little bit about what that technology is early on. But a lot of the focus of this presentation is going to be on one of the early applications that we think our battery is a great fit for. And that is in basically the new type of geothermal energy. And there'll be quite a significant discussion of what this is in later slides. But essentially, a lot of geothermal exploration as it becomes more and more mature technology and an expanding technology in the market looks a lot like oil and gas drilling, just under more extreme conditions. And so part of that is basically taking the tools that people have used for oil and gas drilling and, if you like, repurposing them for good for more renewable technology. But because the conditions are so different, you need a whole different set of operating tools, including power sources. And that's where we see a really good fit. So I'll talk about batteries first, but really I would like you to understand also why we think we're a good fit for this expanding new geothermal market. And Zeming can lead a lot of that discussion. So as I said, we're a battery company that came out of some work that myself and unfortunately the late Bob Grubbs did while I was at NASA's Jet Propulsion Lab, and he was at Caltech back in the kind of late 2010s, essentially dealing with fundamental electrolytes and reaction mechanisms and materials for a new type of battery chemistry that relies on a different way of doing things than lithium-ion chemistry. We've since, raised some of the seed money through Freeflow and some other interested early stage investors, with the kind of goal of demonstrating some of these fundamental technologies and understanding some of the basic battery functions that we can enable through these types of technologies. So currently we're, a limited team, myself and Zeming, and sponsoring some research at a bunch of different laboratories, including JPL and the University of Southern California, currently working on all sorts of aspects of this fluoride-ion battery technology. So why is fluoride-ion battery of interest? I'm sure you all know a little bit, or maybe a lot, about lithium-ion batteries, right? They are because lithium is at the top left of the periodic table. It's fundamentally very light, very electropositive. So you can get a lot of energy out of batteries that use lithium as, in a lithium-ion battery as the charge carrier, in a lithium primary battery as the anode material itself. Because lithium is light, has a very high potential because of the electropositive nature of it, it translates to a very large specific energy and energy density in lithium-ion batteries. And so batteries are light, run for a long time, They're being used in electric vehicles, portable electronics, all of these things because of these fundamentally good energy and mass and volume behavior of lithium systems. But as the lithium-ion market has expanded over the last decade or so to cover electric vehicles particularly, we start to worry about the resource availability for some of these lithium-ion chemistries. There's some cathode materials involved that come from politically unstable and potentially dangerous places. Lithium itself is somewhat resource constricted. People are trying to find new mines all over the world at the moment to try and meet that demand. And if you look at the trends, you kind of realize that if electric vehicles become worldwide at the adoption rate that people project, there might not be enough lithium-ion batteries around to do all the other things that we're used to having lithium-ion batteries do, charge yourself, power your cell phone, power your laptop, and so on. So we need to start looking at other types of chemistries that can potentially provide that volume and high energy and lightweight kind of profile that lithium-ion batteries do. Nobody wants to have a cell phone that's powered by a lead acid battery like they used to do in the early 80s, right? So we need to evaluate these alternative chemistries with a view to making them as high energy and as lightweight and particularly as resource available with abundant materials as possible. So people are looking at sodium, people are looking at potassium. What we're doing, taking a look at the periodic table and saying, okay, lithium's at the top left. What about the top right? This is where fluorine comes in. Instead of being the most electropositive element, or in terms of, we are now working with the most electronegative element. So instead of moving positive ions around on charge and discharge as you do in a lithium system, we're moving negative ions back and forth on charge and discharge. Basically taking the same kind of concepts, but applying it to electronegative systems rather than electropositive systems. Fluorine is very small. Fluorine is very lightweight, so we can translate some of those advantages for the lithium system analogously to a fluoride-ion system. And we have some significant advantages if we're working with fluoride-ion materials than some of the lithium materials, because we have similar energy, because we have similar potentials of these systems, and particularly a much greater abundance of these materials in nature than for some of the lithium materials. Calcium fluoride is widely available throughout the world, particularly significant deposits in Canada and Mexico, and orders of magnitude more abundant than lithium and some of the lithium associated metals in these systems as well. So if we can get the performance out of these systems with the high energy associated with fluoride transfer reactions, the high abundance and potentially low cost and availability of these materials, we can really imagine a competitor for lithium-ion systems based on this chemistry. The challenge with fluoride-ion chemistry initially is getting it to work, and that's what myself and the Grubbs group figured out. I'll talk a little bit later on about that on the next slide. You can see for a lithium-ion system, there's basically three important components: an anode, a cathode, and an electrolyte. The anode and the cathode do the electrochemical reactions. Lithium can be the anode in the primary battery case, but you've got to move the ion between the electrodes. For lithium, that's pretty straightforward. You take a lithium salt, you dissolve it in a solvent, you make a lithium ion that's mobile, you can transfer that across. You could think maybe for a fluoride system, you could do the same thing, take a fluoride salt, dissolve it, the fluoride moves back and forth in the same way. But the challenge is fluorides are a lot less soluble than lithium salts, and the fluoride ion itself is pretty reactive. It's pretty basic, it's pretty nucleophilic. And so all of the solvents that you try and put these things into, it either won't dissolve or it'll react with it, or it'll do some side reaction that enables it, well, stops it being able to transfer the fluoride on charge and discharge. So a lot of fundamental work, Bob and myself were both chemists, went into trying to tame this fluoride ion to make it soluble enough, but stable enough so that you could get a high concentration of fluoride ions in the liquid, enabling it to do this type of electrochemistry. And this work took a couple of years, but ended up in a pretty nice paper that was published in Science back in 2018. You can see here, working with particularly with Tom Miller at Caltech as well. We found a class of solvents that have a specific structure that enable you to dissolve salts of a particular type to make this electrolyte that looks a lot like a lithium-ion electrolyte now. It has high conductivity, high stability, and enables us to do these fluoride cycling reactions, really demonstrating a fluoride-ion battery for the first time that operates under similar conditions to lithium-ion batteries. There have been fluoride-ion batteries previously that work in the solid state, but if you know anything about solid-state electrolytes, you know that they only operate at high temperatures. And so, nobody wants a laptop battery that works at 150 degrees C, right? To enable room temperature operation of these things, you need this liquid electrolyte. And that's the enabling piece that Bob and I came up with, also with Tom, filed a bunch of patents on, and then gave us the confidence to say, okay, we've got this electrolyte piece understood. Let's try and get the rest of it done. Let's start up a company. And that's where Freeflow come in, and where really the origin of Flion comes from. So we've been able to develop this a little bit to understand some advantages that we can have, right? One thing that we can do is, work with systems that are outside of the operating capacity of lithium systems. So we're able to go, for example, to higher temperatures, and that's where the geothermal piece comes in later. We also have a bit of a safer system compared to a lithium battery, because we're working in certain cases with fluoride materials that are solid, that don't contain some of these, hard to access and, potentially very expensive, rare earths and other, oxide materials that are, a little bit harder to see a sustainable pathway to. The solvent itself is actually a nice stable material, not corrosive. And all of this ties together to give a battery that looks a lot like a lithium-ion battery in terms of its performance, but has advantages from using these different materials, really opening up that kind of sustainability space in terms of the battery materials. So the battery market itself is huge, right? It's gone up at least 10x since I was last involved in this about 10 years ago. $24 billion is a current estimate of that. And most of that is rechargeable batteries, right? So if you think about, lithium-ion batteries now charge and discharge many hundreds of cycles. A lot of work went into making lithium-ion batteries that high tech. They were first commercialized by Sony in 1990. They were first discovered, if you like, by Stan Whittingham in the late 1970s. So there's a kind of 15-year development cycle that is necessary, really, at least. And then an additional 10 or 15 years, we can put them in cars. So, it's a long time. And a lot of that is materials discovery, engineering, and then kind of optimization. So for us to come in with a fluoride electrolyte and say, okay, we got a car battery is a bit of a stretch, right? There's always a development process involved in getting these rechargeable batteries to work as well as we do. And that's where a lot of the work that we're doing with people like USC and academic groups is focused on, really understanding the materials and putting the stake in the ground to get that rechargeable battery working. But a much closer market to us and a much simpler market to address from a technology perspective is the primary battery market. If you think about a primary battery like a AA battery, a single-use battery, a lot of those are, consumer batteries and disposable, but there's a significant fraction of the market that are quite sophisticated, industrial batteries, sensor batteries, long life things where you want to, put it in some kind of, a gas meter and then, go scan it every 6 months, but only change the battery every 5 years kind of thing. And with the advantages of lithium in the energy density space, a lot of these are lithium primary batteries where you have a lithium anode and they last, 2, 3, 5 years. That's actually a not insignificant market. There's about a tenth of the size of the rechargeable battery market, but something that would actually be quite a juicy thing for an early stage startup to be able to get a piece of. We've actually been able to take our fluoride ion chemistry and demonstrate that it actually has substantial advantages over the lithium system. Recently published a paper on this in the Journal of Physical Chemistry, showing that we can take fluoride materials and operate them as a fluoride ion battery to give energy advantages over the lithium primary batteries. And more importantly than that, there's a very specialized market that includes this geothermal market, where the operating conditions are such that even normal lithium primary batteries cannot work. For example, lithium melts at about 180 C. So if you want to do high temperature batteries at 200-300 C, you can't use that lithium anode anymore. So it gets really challenging in terms of thermal management and safety. Some of these fluoride materials that we're working with are stable and are solid and remain safe at these temperatures. And so what we're looking at is taking the knowledge of the electrolyte, the advantages of the fluoride materials in terms of energy and abundance, and putting them in initially in this specialized high temperature primary market, expanding that into the whole lithium primary market. And then as part of that work, understanding the rechargeable chemistry so that we can eventually address the rechargeable battery market as well. But it's really, let's play to our advantages. We have the stable materials, we have the high energy materials. There's a need in this high temperature market. That's where we're going to make our first product. I'll turn over to Zeming now to discuss that a little bit in more detail.
Yeah, thanks, Simon. So naturally, when we went out to find our best market fit and the best use case, geothermal field really stands out for us. Not only because it itself represents a huge, sizable market with 6 billion and a fast growth rate. It also have two unmet needs that currently really fits its revolutionary status. So currently, the geothermal field requires battery that potentially can give a high temperature profile, which kind of fits what we are giving with Flion's energy battery. And secondly, they need a higher battery with a higher temperature battery with a much better safety profile, which is very crucial when they're going into these drilling missions. And I'm going to talk to you about what revolutionary is happening right now in geothermal that lead to this. So first, in terms of traditional geothermal system, people has been exploring the aquifers that is right beneath the ground and utilize it for heat conduction to get energy out. And to do that, people use drills mostly adapted from a traditional oil gas drills. However, next slide, please. With the newer type of geothermal energy budding out, showing here EGS and AGS, they represent a more efficient geothermal energy. And their type of exploration requires a better, more precise exploration tools. For example, so both of them can have to go very deep beneath the ground to utilize the energy more efficiently. So that means, next slide, that in terms of the current technology, it is not sufficiently enough for them to do this type of exploration. And number one is because they require more depth, as opposed to the traditional geothermal exploration, which is less than 5 kilometers beneath the ground. Now we are going beyond 5 kilometers to even 20 kilometers, where it's even higher temperature requirement for the drilling tools. And secondly, they definitely need a more reliable power source to enable these type of measure while drilling applications for them to further explore the field. So now we talk about what we can offer. So as I mentioned before, temperature is the key here. Without a battery that can withstand high temperature, they can't able to go really deep beneath the earth to really get an energy out. And compared to the traditional type of batteries, you can see Flion batteries can potentially operate at up to 350 Celsius, which meet the need of the new geothermal temperature requirement at 170 to 500 Celsius. And this is way above what current battery can afford, which is merely at around 130 degrees Celsius. And anywhere beyond that, they face certain safety issue. So if I can see in this slide, Flion's energy battery can afford this high temperature profile because of the innovation that's been put into this technology here. On the right, we can see the three standout things. First, the solid cathode. Second, the stable anode. And third, safety electrolyte can both yield a much better safety profile at a high temperature utilization compared to the traditional batteries in the current field. On the second side, I talk about the power source. So the current power source that's powering the drills are mainly from the turbine power source. And the turbine power source utilizes mud's mechanical flow to create electricity. So the electricity doesn't come from the inherent battery. However, this represents a huge problem. And as many KOLs mentioned, the turbine power sources are expensive and not reliable. And this potentially can increase cost and decrease reliability due to the drill. And why is that a problem? And if we look at the next slide, we could see the drill itself represents a huge cost of the geothermal project. And the drilling cost is a primary target for the cost reduction. So we, as a new innovative battery tech, can solve two cost reduction issues. First, we can reduce the cost of the drilling time because a fail of the turbine or the battery can lead to a potential drilling downtime and the actual operating cost at about 50 to 1,000K per day. And that is excluding labor costs. That is a sizable amount for any drilling companies. And second, if the turbine cells really fail and beyond the point of replacement, the replace of the turbine source as a whole can cost up to 100 to 200K. And that can be replaced by the Flion Energy battery and can really start the cost saving initiatives for the companies. So what are our potential targets here? So we see three groups of customers for us. So first is the geothermal operators that are involved with the development operations of this geothermal energy project. Second is the geothermal service companies that lend their drill to these operators, right, to conduct their drill service. And third is the drilling contractors, and that actually do the field work for the operators. So all those people are our potential targets. So next slide will just give you a grand view of what are the companies out there. And they're basically lying in these four different fields, either geothermal energy producer or drilling tech, either in the oil and gas field, but predominantly the geothermal only field. And here I want to highlight two specific companies, Yaver and Fervo. So both companies are new innovation groups with their startup status. And if we can see in the next slide, both are targeting the more revolutionary geothermal field, which is the EGS and AGS. And you can see both companies have already raised a sizable amount of fundings in the past years, just due to the growth of the field. So even though geothermal as a very niche field is kind of in the small sector of the high temperature battery field, but it withstands a high potential with the coming development that's going on in the geothermal field. And that presents a great opportunity for us to go into. So with that being said, I'll hand the mic back to Simon to talk a bit more about the current development that we're having with the Flion Energy's tech.
Yeah, thank you, Zeming. So where do we stand now? So a lot of this work is going on at JPL, where they have experience of working with high temperature battery components and assemblies and testing rigs, right? So we were able to demonstrate performance. Actually, we've got recent results at 200C, where we're pulling out, substantial capacity from our fluoride materials. If you think about, capacity in milliamp hours per gram for a primary battery, well, for a lithium-ion battery, you might be around 200. A primary battery, you might be around 300 to 350. We're able to get out almost 600-700 out of our systems at temperature from some of the more recent results. But part of this is engineering limited. What we want to do is not necessarily solve an engineering problem in an R&D project. What we want to do is convince one of these drilling partner people that we should get some kind of joint development work going with them so that we can put our technology in the format that they're able to use in the field. And so we're doing basically proof of concept stuff to show them that it works at these temperatures, and we're having some good success there. Working with JPL also opens the opportunity for some other technologies that they've been working on for example, Venus missions, very high temperature batteries, 500C, and showing that we can even address the higher end of this with some of their technologies if required. So we can go to the drilling companies and say, hey, we've got a, if you like, intermediate range battery from like room temperature to 300 or so. And then if you want to go above that, we've got a second solution for you too that's there. The fluoride materials are going to be stable up to about 350. going beyond that, you need also fluoride materials, but a different electrolyte. And we can kind of bridge both of those gaps with some of the work that we're doing at JPL now. So, I would love to show you an actual finished cell, but we really need some more specifics from the end users to design it in that particular format. And that would be a project that we're looking to start next year once we have all of our work finished at JPL at these different temperatures that we're targeting. I think we'll probably get to about 250 in the lab. It gets pretty tricky to do that without specialized testing equipment. But certainly the thermal stability of everything we're dealing with is good to at least 350 C in our simple electrolyte formulation. And that's kind of the summary of where we are and why we're doing, and hopefully was interesting, and I look forward to answering some questions. Thank you very much for your time.
Thank you. Yeah, and just a reminder to the participants, feel free to put any questions you have into the chat feature, and we'll get those answered. And you can probably stop the screen share now too. But the thing that I always love to start out with is just because I'm just very interested in the scientist journey. Is you and Bob are collaborating on this research, perhaps more from an academic perspective, and then at some point the light bulb goes off that, wow, this actually might be able to be translated into a company, and I know that Simon, you've actually been founder of a few companies along the way, but just I'm curious, like, why did this? Because I think the geothermal stuff has been a more recent development or more recent kind of aha moment. But like when you're in 2018 publishing, et cetera, I mean, and we funded, I believe it was in early 22 when we did a pre-seed. So you guys are, just so everyone knows, on the spectrum, you guys are like, still a very early kind of, company in your development cycle, but it made a ton of progress. But I'm just curious, like, why'd you decide to take this one out, start a company around it, and some of that origin story of the company?
Well, yeah, thanks for the question. I'll give you an even more technical place to start, right? When I was talking about lithium electrolytes being easy and fluoride electrolytes being difficult, right? Both Bob and I are organometallic chemists, right? Which means, you're working with metal things, but from an organic perspective, right? So you're all fundamentally trying to get things to be compatible with other things that are do not like each other fundamentally. So there are tricks in organometallic chemistry to make things dissolve in things that they shouldn't, and all of this. So looking at this challenge, we thought, I bet you we can use our organometallic toolbox to kind of make this type of electrolyte. And it took a bit of optimization, but we nailed it, and we're like, that's a really elegant story of how to kind of turn some fundamental chemistry into something that can be applied, right? Let's run a lithium ion but backwards, kind of, right? So and then looking at that and looking at the growth of the battery market and the explosion of lithium ion research everywhere, right? We thought, everyone's doing so much in lithium ion and associated space that they're probably overlooking some low-hanging fruit in some other areas, right? And so you run the numbers for fluoride and you see per dollar per kilowatt hour and all of this availability of the materials. If we could get this to work, it would be a real significant game changer, maybe even better than lithium ion, certainly competitive for a range of different applications, right? So that, having worked in a battery company before as well, I kind of thought, I vaguely know how to do this. Let's get that critical mass together and actually focus on this and take that cute discovery from an organometallic chemist perspective and turn it into a functioning device and then into a functioning product.
Yeah. And then I'm curious about or just your, and I know you touched on this a bit, but the thing that's always stuck with me is not, there's the applications for this, the high temperature, and there's also just the reality that to date we just seen, and I know we talked about this in the green room, if you will, before we were chatting about this presentation, but just the fact that we just seem to be lithium centric or myopic almost society, and just some of the maybe just comment on that and just some, maybe expand on some of the problems that is, that they're there in terms of where those are found, the limits that they provide, or that they have technically, um, just even the amount that our, planet has,
Yeah.
just those types of things, were just eye openers to me, because people talk about the energy transition, all this stuff, but like there is and that's the demand side, but there's a supply side, like that's just a practical reality of just the materials that we have. And yeah.
Yeah. So the two components of the battery, I was talking about the anode and the cathode. For the cathode side of things, in the vast majority of lithium, high energy lithium systems, they use metals like nickel, cobalt, which are geographically limited. Cobalt is typically found in Africa, maybe some in Australia too, but Congo is not a nice place to operate. I mean, politically and practically and everything else, it people look at it was like blood diamonds, but like blood cathode material, right? And then the vast majority of the world's nickel reserves are in Russia, so that's also challenging to access, right? So there's elements of that. People are looking at iron-based cathodes for power tools, and Steve knows this from A123, but you're not going to get the energy that you get from the nickel and the cobalt materials in that sense, right? So you run into geopolitical issues with that and abundance issues. And on the lithium side, maybe less geopolitical, but certainly the abundance of things is challenging. There's a famous plot from when they put the Gigafactory in Nevada together, where they were going to ramp up to however many terawatt hours over the next decade, and then people said, but there's only this much lithium in the world to do it. So where are you going to find that extra 40% that you need, right? And people are mining and discovering more every day. But fundamentally, the abundance of the materials that we're looking at is 1 or 2 orders of magnitude greater than that, without a lot of that geopolitical headache as well. I mean, I wouldn't consider Mexico under the same headline as Russia or Congo, right? So you can dig up a lot of calcium fluoride. You can dig up a lot of the cathode materials that we're using from in North American abundance, particularly in Canada. Actually, there's some good reserves of that available. And because you're working with high energy, high voltage systems, the relative amounts of material are about equivalent too. So you can literally look at those abundances and say, okay, fluoride is 100 times more abundant than lithium ion systems, for example.